Today we're going to look at volcanoes. Now if you want a definition, a volcano is a break or an opening in Earth's crust through which lava, ash, and gas can escape. And I think that's interesting because we tend to think of volcanoes as just lava, but really there are lots of volcanic eruptions that erupt only ash or sometimes even only gas. There's a beautiful shot of some of our local volcanoes. This is the San Francisco Peaks up in Flagstaff. So this is actually an ancient volcano. It's extinct, which is good news. And in the foreground of the picture, you can actually see some other little ones. This is looking towards Flagstaff from the Mormon Mountain area. So we're going to look a little bit more at these. So volcanoes are going to occur mainly on tectonic plate boundaries. And they happen at certain ones, right? So they can happen because of decompression melting, and that is at divergent plate boundaries like the mid-ocean ridges or like the East African Rift, or even some of our volcanoes from the Basin and Range province. It's also what drives hotspot volcanism as well, like we see in Hawaii, like we see in Yellowstone, like we see over here in Cameroon and Iceland. Melting can also occur because of volatiles being introduced in the mantle through subduction zones. And so that's pretty much your entire Pacific Ring of Fire. And that's where we have most of those volcanoes, is from those specific locations. Now, before we talk about volcanoes too much, I want to talk just a second about fluid mechanics. Because lava is a fluid, and so it flows. Now, viscosity is the way we describe how a fluid flows. So viscosity is defined as the resistance to flow. So something that's resisting flowing doesn't want to flow very much. So if it's more viscous, it resists it a lot. So in this case, this is this test tube on the right. This has got a high viscosity. It's resisting flowing. Versus here on the left, it's much, much runnier. And so that's got a low viscosity because it's not resisting flowing very much. So in this case, something like water is going to have a really low viscosity, and something like peanut butter is going to have a high viscosity. Now, in terms of materials that you're going to be seeing in volcanoes, our low viscosity looks a little bit more like this middle stuff. So when you think low viscosity lavas, I want you to think of like pancake syrup. And when you think of high viscosity lavas, I want you to think of like toothpaste. Alright, so because that's pretty similar to our viscosities. Now, viscosity of lava is going to be set mainly by three things. Number one, the composition of the lava. So on Bowen's reaction series, it's been a little while since we talked about this, right? The composition is at the top of Bowen's reaction series, this mafic. We won't really count ultramafic just because there's no ultramafic lava flows. But we do have lots of mafic lava flows. And so mafic's going to be our lowest viscosity lava. This is going to be the really runny stuff, right? And part of that is because the structures that we find in those mafic lavas are very simple structures. And so if you have just a bunch of chains, they slide past one another a lot easier than these big nets and these big sheets do. All right, so mafic is the most viscous, or I'm sorry, the lowest viscosity, and felsic has the highest. The second thing that's going to affect your viscosity is going to be temperature. So as things cool off, they tend to get more viscous, which makes sense, right? If you think about it, a milkshake is really cold and it's really thick, versus like a glass of milk, which is not nearly as cold and it's not nearly as thick. Right? So temperature. So the colder it is, the more viscous it tends to be. And finally, dissolved gases. If you have a lot of water or carbon dioxide dissolved in your magma, that actually tends to make it a little runnier. All right, so we're going to look at how this affects our eruptions, because a really thick lava traps gas really easily. And the key to an eruption is just how easily that gases can escape from the lava. when it's really viscous, the gas can't escape very easily. And so when it finally does, it erupts really big and really explosive. Versus a low viscosity lava that's going to let the gas escape really easily, and it tends to be just kind of nice and flowy and fairly gentle. And that's why you can go on vacation in Hawaii while the volcanoes are erupting, and you don't have to worry about things too much. It's very low viscosity flows. Versus, say, Mount St. Helens back in the early 80s. You wouldn't want to be vacationing there at the time because the lava is a lot more viscous. Now, the lava's viscosity is also in part going to give us the shape of the volcano. So if you have a really runny lava, really low viscosity, it runs out really far away from your vent, so you end up with really wide, really gentle sloping volcanoes. Andesite is going to be just a little bit thicker. This is your intermediate lava. Your andesite is going to be a little bit thicker, so it won't flow quite as far, so you tend to get a little bit steeper slopes. And then finally, your most viscous, your rhyolite, doesn't flow at all. Like I said, think toothpaste. And in this case, your toothpaste doesn't flow very far at all, so you get these really steep-sided volcanoes because of that. So let's look at some examples of volcanoes made from each one of these materials. We're going to start with the basalt. We'll start with the gentle stuff and work our way up. So these are going to be basalt lava flows and volcanoes made from that. Our main one is the shield volcano. Now where this gets its name is if you imagine this Roman soldier here. If you were to take that shield and lay it face up on the ground, it makes this really kind of gentle slope to it, which is exactly what a shield volcano looks like. These are actually kind of hard to recognize as volcanoes. These are the largest on Earth. They can erupt for millions and millions of years, and a single eruption can go on for a very long time. For instance, Kilauea has been erupting for over 30 years now in one single eruption. Now those eruptions create lots of lava flows. So we get two varieties of basalt lava flows. First is called an A'a flow. It's a Hawaiian term. You can see it's blocky lava. So it looks like these big kind of chunks rolling against each other. Let's see, I think I've got a video here for you. Now keep in mind, basalts are low viscosity, so this is actually fairly runny. And if you can hear the tinkling noise, that's actually what we call Cinder. It's the little pieces of water running in each other. And on an old A'a flow, sometimes you can still hear that tinkling, which is pretty cool. As you can see, the two men in that previous picture weren't in a very big hurry to walk away, because you can walk away from these pretty easily. Now your lower viscosity is called a pahoehoe flow. So pahoehoe, or ropey lava, tends to cool on the top, and then the top of it kind of curls up against each other. Well, it's going. Oh, it's really hot. Did you dip your hammer in now?
You want to do it?
You're done?
What?
Almost a geologist talking about.
You have long sleeves?
Yeah, I can put them on right now. This is a little bit lower viscosity, so still pretty easily outrunnable at this point. Good grief, that's scary looking. But you can see just how slow this can actually move. Now, when that pahoehoe flow crusts over the top, it can create what's called a lava tube. So the top of it crusts over, but the inside is still nice and gooey and flowy. And basalt's a great insulator, so you end up getting these tubes of underground lava that get carried for very long distances away from the vent. This is one of the ways that your shield volcanoes get so big. And what happens is, once that lava drains out, it sometimes leaves the tube behind. So this is the Thurston lava tube here on the screen on the big island of Hawaii. So that used to be full of lava, and you can walk through it now. We actually have one of these in northern Arizona. There's quite a few, but there's a famous one, or a really well-known one. It's called the Lava River Cave. And so you can actually crawl down and hike through it, which is a pretty popular hike if you're up in the area. It's pretty neat. Now here's some of my favorite lava tubes. This one is Hadley Reel. This is on the moon. And here's some lava tubes on Mars. And in this case, what we think is an impact left this crater behind, and it happened to punch through the top of a lava tube. So you can see down into it. How cool is that? So this is one where we get caves on other planets. Now when basalt lava is erupted underwater, it creates what's called a pillow lava. Display here. I'm going to zoom forward a little bit. This is some really cool footage from a dive company in Hawaii. So this is what it looks like when lava erupts underwater. At least the salt lava. As you can see how it's very neat. But you can see these like bulbous shapes. This is why it's called pillow lava. So if you ever see pillow lava on the surface, like old pillow lava, like you see in the picture here, that's a good indication that you had basalt flows underwater at one point. So let's look at some examples of shield volcanoes. This is Mauna Loa in Hawaii. All the big Hawaiian volcanoes are shield volcanoes. You can recognize Mauna Loa because you can see the observatory at the top there. Means long mountains, one of the longest and largest mountains on Earth. One of my favorites, Olympus Mons on Mars, is actually a shield volcano. Now, our largest volcanoes on Earth are all shield volcanoes, but on Mars, they grow a whole lot bigger. For instance, Olympus Mons is about the size of the whole state of Arizona, which is massively larger than even Mauna Loa, which is just one of the volcanoes on the Big Island of Hawaii. Now, these basalt flows, when they're really, really runny, they create what's called a flood basalt. And so really, really runny ones create flood basalt. So rather than a volcano, it gets stacked up into layers. And these are from the Columbia River basalts that are in Washington State. Now there's one more type of volcano. So we've looked at shield volcanoes. There's one more type of volcano that's actually made out of mafic material, out of basalt, and these are cinder cones. So in this case, cinder cones are one of the smallest volcanoes. They don't last very long. Usually they erupt about a year and then they stop erupting and they never erupt again. They're called monogenic. So in this case, what happens is little bits get blown into the air. They cool as they're in the air and they fall back down. And it's basically a pile of scoria that's like the size of walnuts, as all these little guys are. So that material getting thrown up in the air, we call that pyroclastic material. So pyroclastics can be those tiny little cinders that are, like I said, the size, like pea size to walnut size, all the way up to blocks and bombs. And I'll show you some examples of volcanic bombs in class because they're pretty cool. But some really big stuff actually gets thrown out of the volcano sometimes. Now here's some examples of some famous cinder cones. Here's Arizona one, Sunset Crater. It's a national monument. The name comes from this lovely color at the top. You can't hike Sunset Crater because it is protected at this point, but it's quite lovely to go visit. You can hike SP Crater. You've looked at this in lab. It's one of our most famous ones. And it's super photogenic. Because it's really symmetrical and it's got this perfect kind of hole at the top and there's beautiful lava flow coming out of the north side of it, which is why it gets used as examples all the time. We also have Pyroclastic. It's a cinder cone in Mexico. It started erupting back in the 40s and it actually erupted for about 9 years. In that time, they had to relocate a couple of little towns even. But this is a great volcano because it's the first time volcanoes were able to be studied from the birth to the death. The whole way through the series. One day there was a farmer that had a cornfield and there was a big crack in the field and ash started coming out of it. And like a week later there was a volcano that was 300 feet tall. By the end of the eruption, that volcano was over 300 meters tall. And you can see it now. It's kind of cool. But here's a shot of it mid-eruption. All right, so those tend to be pretty gentle eruptions. People don't tend to die. They tend to be fairly safe. Like I said, that's why people can go on vacation in Hawaii, but then they get scarier. All right, so we have andesite and rhyolite flows. I'm going to show you both of these. So andesite lava tends to create stratovolcanoes or composite cones. Strata in geology means layers. And that's because these volcanoes are created from alternating layers of lava flows and tephra, which is basically ash. So you get a lava flow and then ash and then lava flow and ash. So you get fairly gentle eruptions of lava flows and then explosive eruptions with lots of ash, and then fairly gentle and then lots of big explosive ones. A composite is something made out of two different things, and that's that ash and lava flow kind of feel to these things. Stratovolcanoes are the most deadly volcanoes on Earth because they are fairly viscous lava. They tend to be pretty explosive, and there's a lot of them. Now, these happen almost exclusively at subduction zones. There's a beautiful example of Mount Fuji. So these are pretty easy to recognize because they tend to be really nice, pointy, really tall mountains. And I always when I draw these on the board, I put snow on the top because they tend to be tall enough that they almost always have snow. Like I said, these haven't converged to plate boundaries. These are our subduction zones. So great examples of these are through the Aleutian Islands, the Kamchatka Peninsula, all the way through Japan, and even ours along our subduction zone in the Pacific Northwest. So Mount St. Helens, Mount Hood, Mount Baker, Mount Shasta. Those big ones there, those are all going to be composite cones. These are, like I said, created by andesite lava flows. Here's some pictures of some andesite flows. You can see they're pretty stubby. They don't go nearly as far as those basalt flows do. But because they're so explosive, they create this. So you see it looks like a nice fluffy cloud making its way down the side of the volcano. That's pretty much death right there. That's all it is. It's a very scary thing. This is called a pyroclastic flow. And pyroclastic flows can form when you have an ash column. So eruption starts erupting, and eruptions are all about gas. So lots and lots of gas pouring out, and it's shooting ash up into the air as high as it can. And then all that ash starts falling back down, and then it falls down and collapses and flows down the side of the volcano as this pyroclastic flow. Here, I'm going to play this video and I'll keep talking for you. So this is a pyroclastic flow on Sinabung. This is in Indonesia. You can see these lovely fluffy white clouds coming down. So this is a mixture of ash and gas and rock, and it's moving very fast. Depending on how the eruption happens, these can move up to 150 miles an hour, which means you're not going to outrun them. They're also very hot. You're looking at like 12 to 1800 degrees, which means if it reaches you, you're not going to be able to survive it. Now, ash is worth talking about just because ash is actually pulverized pieces of rock. It's actually tiny, tiny shards of volcanic glass, which makes it even scarier as it's coming towards you, doesn't it? Now, this is a major cause of death for in a lot of volcanic eruptions. So let's look at some famous stratocones. For one, Mount St. Helens, this is before 1980. Beautiful, nice, pointy shape. That's indicative of those stratovolcanoes. Got snow at the top, lots of glaciers. This is Spirit Lake down here, lots of camps around there. And then this is what all that looked like after that eruption. This was an interesting one because just the whole side of the volcano blew out, which was bizarre. You see a famous quote from this: "Vancouver, Vancouver, this is it." This was the famous last words of a gentleman by the last name of Johnston who was monitoring the volcano, and he saw it erupting and called into the USGS right before that pyroclastic flow hit him. Now, Mount Vesuvius is in Italy is a stratovolcano, best known for being the cause of death in Pompeii and Herculaneum. And we'll talk a little bit about these bodies in class because they're pretty fascinating. But it was probably a horrible, terrifying ordeal. You can see all the people huddled against the wall, sort of up in the fetal position. The doggy here, he did not make it, obviously. And all of these folks were killed by pyroclastic flows coming down through town. And this is what the volcano looks like today. So this is basically Naples. There's between 2 and 3 million people who currently live along the base of Mount Vesuvius, and this is considered to be the most dangerous volcano in all of Europe. Now, that eruption that killed everybody in Pompeii happened in 79 AD, but that's not the only eruption of it. So here's some paintings of it erupting at other times. So 1770 and 1771 eruptions. Here's a photograph from 1872. And of course, this was in the 40s as the Allied troops were going into Italy during World War II. The volcano was actually erupting, which is just kind of mind-boggling. So there's lots of pictures and lots of footage from that. Some other ones, this is Mount Pelée. This is on the island of Martinique. It's in Martinique. This is the town of Saint Pierre. And in 1902, Mount Pelée erupted and shot a series of pyroclastic flows down into town. And this was what was left over. And it basically killed everybody in town except for one guy who was a prisoner who happened to be in a isolation cell. And that's the only reason why he survived it. And this is the town today, sitting at the base. So this was that entire burned out area in the last picture there. And finally, we have our volcanic domes. So volcanic domes are going to be created by rhyolite. They tend to be very steep-sided, but they're really dome-shaped, which is where the name comes from. This is Mount Eldon and Flagstaff. Now, the key to domes is they're fairly unstable. So what happens is they grow and grow and grow, and then they blow up in a rain of fire and pyroclastics, and then they grow again and blow up and grow again and blow up. And Mount Eldon is no different. There's some beautiful pyroclastic surge deposits around town from when this was erupting. My very favorite volcano is Mount Lassen in California. It's the largest volcanic dome in the world. This is actually one of my photos I took when I visited. The reason why is it actually erupted not that long ago. It actually was erupting in like 1915 to about 1917. And you could see the eruptive cloud through a lot of northern California and into Oregon, which is why I think it's pretty cool. Now here's an example of a plug dome. So this is like really, really thick lava that's left over after a big eruption. So this is actually what's called Mount Pelée Spine. So this is Mount Pelée from Martinique, the stratovolcano. And after the eruption, this kind of shot out the top of it and grew really tall. And then it blew up, so it's not there anymore. And just like stratovolcanoes, volcanic domes can lay dormant for quite a while in between eruptions. Here's a dome inside the crater of Mount St. Helens. So you can see here's a couple of domes that actually formed on a stratovolcano. That's okay, it happens sometimes. Panem Crater, this is in California, right near Mono Lake, kind of in the northern edge of Owens Valley. But that's a beautiful little dome that's surrounded by a tephra, so lots of ash, lots of scoria all the way around it. Now the big daddies of all volcanic eruptions, these caldera or quote-unquote supervolcanoes. So basically a caldera is a giant hole. So one of the most famous examples is Crater Lake in Oregon. So Crater Lake actually started out as a stratovolcano called Mount Mazama. And it started erupting. So big scary eruptions just like we're used to seeing from stratovolcanoes. Lots of ash, pyroclastic flows all over the place. People running for their lives. And what happened is it erupted so much it actually partially emptied the magma chamber. Now, if you know anything about nature, is that nature doesn't like holes underground. And so nature's going to fill it in. And how they do that is The whole thing collapses down into it. And that's where you have this big crater, that's where the volcano collapsed. And of course, that's still kind of bubbling and sitting there. So as it rains, rain fills in. But that hot material is still kind of moving, and it ends up forming Wizard Island. And Wizard Island is actually a little cinder cone. Let's go back here. There you go. So it's a little cinder cone in the middle of the lake. Now, it's a beautiful place to visit. The water is exceptionally blue because it's really, really clear. The only water entering the lake is coming from rain and snow, so there's no input from rivers, which means there's no fine, like muddy sediment, and very low levels of pollution. So you can see over 400 feet deep into the water, which is just amazing. Highly recommend visiting. Now we have some of these calderas here in Arizona. So here's a picture of the Superstition Mountain that's just east of Phoenix. All of these actually were deposited as ash during an eruption, a caldera eruption. So you can see there's actually 3 separate calderas that in the Superstitions. One around Weaver's Needle, one right around the Goldfield Mountains, and one kind of on the Apache Trail. So this is definitely a place you probably wouldn't have wanted to be like 30 million years ago. Here's another example of some. These are the Chiricahuas down in southern Arizona. It's one of my favorite places in the whole state. Now, a couple of here's some special volcanic features. Because let me draw you a little picture here really quick. A pin. So when a volcano, pretend that's a volcano, is erupting, we just see this stuff at the top. There's some ash coming out of it for you. But below it, there's a magma chamber. So this is kind of where the magma is holding, and then it's generated down below in the very upper part of the mantle. But for that magma chamber, there's usually some sort of tube that feeds up to the top of the volcano. This is that volcanic pipe. So if it clears out, it can leave a pipe behind, which is what you see here. This is actually a really famous one. This is the Kimberley pipe in Kimberley, South Africa. And the reason why this is known is this is a prolific diamond mine, a really famous one. What can also happen, though, is rather than draining out, leaving the hole behind, it fills in, cools off, and that tends to be actually fairly hard and fairly stable, and all the rest of the volcano erodes away. So it shows you what's left behind, and that's the volcanic neck. And if I add a few more things, sometimes little bits of lava comes out the side, and it forms dikes. Now we've looked at what dikes look like left over. So here's an example of a volcanic neck. So you have where the ancient volcano used to be around it, and that pipe in the middle where it filled in and cooled off. And a beautiful example of that is Shiprock in northwestern New Mexico. All right, on top of the volcanoes and the ash and the pyroclastic flows, I want to look at just a little bit other hazards that come from volcanoes. One of them is a lahar. So a lahar is a mud flow on a volcano. So this is Mount St. Helens. And you can see it's erupting. It's hot, so it melts the snow on the top. That snow mixes with ash, and all of that comes roaring down the side of the volcano as this nasty slurry of ash and water. And lahars actually are very, very dangerous. In 1985, there was an eruption of a volcano called Nevado del Ruiz in Colombia. And the town of Armero sat at the very base of this. And a lahar covered the town and killed like 30,000 people all in one fell swoop. So there's some pretty famous pictures of the victims as they were trapped there in that lahar. Now, lahars are made of, like I said, of volcanic ash. And ash actually tends to be super, super deadly. Whether it's in the form of mixed in water and creating lahars, moving down the volcanoes as a pyroclastic flow, or sometimes just a nice gentle ash cloud up in the sky. If a plane flies through a volcanic ash cloud, it can actually shut down the jet engines. And if you are 30,000 feet in the air, you want at least one of those engines working. And so when this little volcano in Iceland started erupting, there's the name of it. It's pronounced that one in Iceland. It's in an ash cloud that actually got picked up by the jet stream and carried over. So it was carried here over the UK, out to the Atlantic. So this jet stream swung back over Europe, up over Sweden, Finland, and down into Russia. And what they ended up having to do is shut all of this airspace down, just on the off chance that volcanoes would fly through it. Um, this isn't the only place it's a problem. The Kamchatka Peninsula here in Russia, it's one of the most volcanically active places on Earth. So are the Aleutian Islands. And these are major, major flight paths between Asia and North America. And that's a picture of a jet engine that's all gunked up by volcanic ash. And we'll probably talk in class about a couple examples of flights that have actually been affected by volcanic ash. Now, because we don't want to, we want people safe and we don't want airplanes flying through those ash clouds, we do a lot of monitoring of volcanoes to make sure we know when they're going to erupt. We can actually tell fairly well kind of when that's going to happen. For one, we look at earthquakes, because there's a couple different types of earthquakes that occur on volcanoes when they're about to erupt. One of the big ones is this harmonic tremor. The volcano basically starts to hum as lava is coming to the surface. The other one is when the lava is actually being erupted, or right before. Sometimes you get this signature here almost at the bottom. This is called a surface event here, but this is commonly known as a tornillo. If you know a little bit of Spanish, that means screw or tornado. And it's for this shape where it starts small and gets bigger and bigger and bigger. And there's some volcanoes that right before they erupt always have those. So we can also look at changes underneath them, because as lava is filling up the magma chamber, and I drew a picture there for you, the whole volcano tends to start swelling. And that's what's going on here. These are the Three Sisters in Oregon. And so this is actually showing how far those are actually rising, which is pretty scary. All right. So that was a quick overview. We'll talk a little bit more about some specifics in class, but at least I hope this gives you an idea of some of the volcano types and the biggest hazards because of those volcanoes.